This video is part of an online course of Calculus 1 and I'm gonna talk about infinite limit. Okay, so we're gonna use the notation lim of f of x as x approaches to some point a is equal to infinity. That's the notation for infinity. If we say that the limit is infinity, this is not actually a number, so it is not a number, just a notation. Okay, so for example, we can say that the limit of f of x as x goes to a point a equals to positive infinity. What does that mean? It means that f of x grows positively without bounds. As x approaches but not actually equal to a. We can say also the limit of f of x as x goes to a is equal to negative infinity if f of x grows negatively without bounds as x approaches to a but not equal to a. Okay, so we have a situation like this, you see, and here when we say that the limit goes to infinity, it means that it grows and grows like this, and the limit goes to negative infinity, it means that it's getting smaller and smaller and smaller like this. So it's going this way down and it's going up that way if the limit goes to positive infinity. Okay, then let me give you a note. The first note is that we have similar definition. We have similar definitions for this situation, that we have the limit of f of x as x goes to a from the right. It could be equal to positive infinity or negative infinity, or the limit of f of x as x goes to a from the left. Okay, actually from the left it could be positive infinity or negative infinity. It means that the function is growing positively as x approaches to a from the left, or in this situation f grows positively without any bounds as x approaches to a from the right. Okay, something else is that in all these four cases, so in all cases the limit does not exist. Okay, but by abuse of terminology we say that the limit is plus or minus infinity. Okay, let's look at some graph and then see what we have. So let me graph 3 functions. Okay, so at x equals to a, our function could go to, you see, from the left it goes to positive infinity, also from the right it goes to positive infinity, and we say that the limit of f of x as x goes to a, it's positive, actually infinity, and f of a is undefined. You see, I don't have the value of the function here. And let's look at the second graph. the point A, we can have also something like this. So the limit of f of x in that case, as x approaches to a from right or left, both of them, it goes to negative infinity. I can also define the function at the point like this and then say that f of a is actually defined in here, and it's equal to the value of this point, the second coordinate of this point. Okay, we can also have this situation that we have it like this, x, y, and in that case we say the limit of f of x as x approaches to a from the right. So this is the point A. From the right, as you see, if we're getting closer to a from the right, it's going to negative infinity, and the limit of f of x as x goes to a from the left, from here, it goes to positive infinity. And based on that, as I said, in all these situations, the limit does not exist. But we can actually specify that it's positive infinity or negative infinity. That's good. But for these functions, since the limits from the right and left are not equal to each other, we say that this does not exist. This limit does not exist. And it's not, let me write this, it's neither positive infinity or negative infinity. We cannot specify because right and left are not equal to each other. Okay, let me give you a remark. And the remark is that if any of these occur, we say that x equal to a is a vertical asymptote. Okay, so in any of these cases, we have a vertical asymptote of x equals to a because the function is getting closer to a, and when x is getting closer to a, the function is going to infinity. That's an asymptote. Let's look at some examples. So let's look at the function 1 over x as x goes to 0 from the right. What is the graph? Okay. The graph of 1 over x is like this. Okay. So as x approaches to the point 0, from the right, this is positive infinity, the limit. How about from the left? 1 over x as x goes to 0 from the left, you see it goes to negative infinity. Actually, let me change the graph so that it looks like an asymptote. It is negative infinity. So the limit of 1 over x as x goes to 0, we say that does not exist. And we say that x equals to 0 is actually a vertical asymptote. Let's look at another example. For example, the limit of tan of x as x goes to pi over 2. Let's look at the graph of tan of x. X, y. So pi over 2, the graph of tan is like this. Actually, the graph of tan is periodic. Okay, but we just consider just one part of it. So I'm gonna remove these ones. And at x equals to pi over 2, which would be right here. Let me actually graph this one as well because I need it. Like this. X, okay. When x approaches to pi over 2 from the right, from here, you see that the value of the function is at negative infinity. And the limit of tan of x as x approaches to pi over 2 from the left, from here, from values that are less than pi over 2, it's positive infinity. So the limit of tan of x as x approaches to pi over 2 does not exist, and x equals to pi over 2 is a vertical asymptote. Okay, let's look at another example like this graph. The limit of ln of x as x goes to 0. What is the graph of ln of x? Just think about this for a second. Let me graph it with this color. This is the graph of ln of x. As you see, the left hand side, the left of 0, is not even on the graph. It's not even on the domain of this function because the domain of natural log is where x is positive. So we cannot even say the limit of ln of x as x goes to 0 from the left because it's not even on the domain. And I just need to consider from the right, and from the right, as you see, it's negative infinity. Okay, the last example, the limit of 1 over x squared as x goes to 0. Okay, 1 over x squared, look at the graph, x and y. Okay, so the graph of this function is like this. So from the right and from the left, both of them, it's going to be positive infinity. Okay, so we have a vertical asymptote here as x equals to 0, the y-axis, and we have a vertical asymptote of y-axis, which is x equals to 0 for ln of x as well in here.